Never be afraid. There's nothing which is known which can't be understood. And there's nothing which is understood which can't be explained. For over 50 episodes now, my team and I have brought you to the very frontier of knowledge in physics and astronomy. And still, our mission goes on. To present you with your birthright, an understanding of the universe. I've traveled the world seeking out a certain type of genius. Masters of not only their academic disciplines, but also at explaining their research in understandable ways. And I've bestowed upon these women and men the title of Titanium Physicist. You're listening to the Titanium Physicist podcast, and I'm Ben Tippett. And now, allez, physique! I've had a particular quote echoing through my mind for quite some time, and it has to do with the moon. It has to do with how intimate an experience it is for two people to look at the same thing together, to read the same books side by side on a couch, or to watch the ducks from a park bench, or to lie down on the grass and stare up at the clouds. I mean, being part of an audience to witness a sporting event can bring two complete strangers together as friends. How much more powerful is this effect among people who actually like each other? So when two people are separated and vast distances keep them apart, they can still look up at the same moon and know somehow they're spending time together. And the moon is actually a lovely object for us to use at the center of this fantasy. Unlike the constellations, which change depending on your latitude, unlike the sun, which will burn out your eyes in their sockets if you try to look at it, the appearance of the moon doesn't change depending on your location. If two people are looking at the moon on the same night, guaranteed they're seeing the same thing. And heck, the moon hasn't really changed over human history either. The moon I look up at tonight is the same moon my grandparents watched. It's the same moon that oversaw the construction of the pyramids. So it's such a sweet and romantic and common image that I was sure as I was preparing today's show that the whole sentiment would come out of a single quote. Bethany suggested that maybe it was the American Tail movie, but I figured it was somewhere fancier. So I Google searched it, and you know what I found? Nothing concrete. Taking consolation from the fact that both you and your friend are looking at the same moon is so old, I have no idea where that sentiment originated. The most interesting quote I found involved the story of Sojourner Truth, an important person from American history. Sojourner was born a slave in New York State around the late 1700s, and when she was 29, she escaped to freedom and spent the rest of her life working as an activist for the abolition of slavery and for women's rights. Sojourner was the second to youngest child in her family, and her parents had had all of their other children taken away from them and sold. Her mother, in her sorrow, used to take Sojourner out to look at the stars and told her that even though they were impossibly far apart, all of Sojourner's brothers and sisters were staring up at the same moon. It sounds lonely maybe, but it's an earnest and hopeful action. Even though we'll never meet, our hearts are still together. I'm looking at the same moon that Albert Einstein watched when he was formulating his theory of general relativity, and it's the same moon that inspired Isaac Newton to write the universal theory of gravitation, and it's the same moon that hung in the sky when slavery was abolished, and it's the same moon when the Universal Declaration of Human Rights was proclaimed by the United Nations General Assembly. Even though chasms of space and time separate us, we can still inherit their dreams. It's a lovely, romantic notion. Too bad it's not quite true. Today on the Titanium Physicist podcast, we're talking about how the moon is slowly shrinking. Oh, weird. Okay. This week's guest is an expert on examining how pleasant fictions can be the glue that holds our lives together. He's a public radio reporter and producer, and he's done things on NPR Morning Edition, Marketplace, and 99% Invisible. He came to my attention with his fantastic podcast, Imaginary Worlds, on the Panoply Network. His show is about the shoreline between the worlds of popular fiction and real people's lives. He interviews people and discusses how works like Harry Potter and Star Wars affect their lives and society in general. Welcome to the show, Eric Molinsky.
Thank you. Great to be here.
Awesome, Eric. For you, I've assembled two amazing titanium physicists. Arise, Meg Rosenburg.
Hi.
Dr. Meg got her PhD from Caltech on the moon's surface. Not Caltech on the moon's surface. She was researching the moon's surface. She's currently a science communicator. Her personal website at www.megrosenburg.com has all her works, and a link to it can be found off of our website. Now arise, Briony Horgan.
Dun, dun, dun.
Dr. Briony did her PhD at Cornell University, and she's currently an assistant professor at Purdue University, where she studies the geology of Moon and Mars. All right, everybody, let's talk about the evolution of the Moon.
I mean, the only thing I know about the Moon in terms of physics is that the distance from the Moon to the Earth is really important. In terms of the tides, that is literally the only thing I know, and that's interesting to me. Like, I just think it's interesting that the Moon is anything more than just a rock in the sky, so I'm curious about that.
But that's all it is. It is just a rock in the sky. But the important thing is, where did it come from?
Yeah, so actually I think people have been wondering that for a very long time. And lots of different types of theories have sort of been proposed over time, resulting in sort of one that we have come to generally accept as probably the right answer. But some of the crazier ones, the leading up to that point, are still really interesting to sort of look back on. So for example, there was once this idea that maybe the Earth, when it was first forming, was spinning so fast that it actually spun out a blob of material that became the Moon. And that's sort of this fission idea. Or maybe the Moon is like a captured asteroid, like the Earth was just going around about its business and an asteroid came by and was captured by Earth's gravity and that became the Moon. Or maybe they just formed together, like in place. Like the solar nebula is where all of the planets condensed and the sun was formed, and maybe all these solid particles just condensed in place and we got the Earth and we got the Moon orbiting it. And then, we were just together forever from the beginning. But what has happened over the years is that we've sort of developed these tests for these theories. We've sort of accumulated little bits of evidence about the Earth and the Moon and how they behave with each other that give us clues as to which of those models or a different model might be the right one. So to sort of introduce the idea that has currently taken hold, we think we condensed from this solar nebula, which is like a cloud of dust and gas, or is originally all gas. And as things started to cool down, this cloud started to flatten out and rotate into a disk. And then solid materials could eventually precipitate out of that and clump together. And all of these little clumps of solid particles would be mutually attracted to each other, either through surface tension or then later through gravity. And eventually those little clumps could form bigger clumps, and then they would start to whiz around and hit each other. And so the theory that has sort of taken hold for how the Moon formed today is related to that idea, where we have these bigger and bigger objects and they're zooming around the solar system, and at the very end of planet formation we would have had just a few of these giant planetesimals, so not quite planets yet, but in that very last round, a very large body like the size of Mars would have hit the proto-Earth, and that giant impact would have spilled off this like plume of material from the Earth body, and that would have eventually recondensed again and formed the Moon. So that's sort of where we think now the Moon came from.
Wait, hold on. So there's a cloud of stuff. Is that cloud of stuff the proto-Earth, or is that the Earth already formed and that's the future Moon?
The cloud of stuff after the collision or before?
Before.
So before there were any planets, we think that the whole solar system formed as this condensing cloud. So it would have been like the sun would have been the hottest and densest part in the middle. And basically, if you have a cloud of anything, a cloud of dust and gas, and it's shrinking over time, if it has any sort of random bit of rotation at all, then that rotation as it shrinks will speed up because of the conservation of angular momentum. And the action of that will sort of flatten this cloud, which was maybe like more like a sphere in the beginning. It'll sort of flatten it over time into a disk. And this disk will be spinning up as it shrinks further and further. And then out of that sort of spinning, collapsing, rotating disk, we're getting sort of solid particles are starting to accumulate together into little clumps. And those are the building blocks of what eventually becomes the planets.
Is that disk like the sort of what we see around Saturn? Could I imagine like a gigantic universe-sized version of that kind of floating material?
There are definitely similarities in the way that Saturn's rings behave and the way that we think that the solar nebula would have behaved. So the reason why they're so flat like that is very similar. And also because of Saturn's massive gravity, it was also sort of keeping them in that midplane. But it is a little bit like that.
The cool thing is that we actually see new solar systems forming around other stars. So we actually have observed this process with, new planets forming out of these giant disks that are around, these brand new baby stars. And so we think the same thing happened in our solar system. And it's kind of like you can imagine, you have this giant cloud of gas, it condenses to form the sun, and it's all of this sort of leftover junk. It's like less than 1% that's left over after the sun forms, condenses to make the planets. And most of that makes Jupiter because Jupiter's gigantic. And then the, 1% of that's left, it goes to make the terrestrial planets, Earth and Venus and Mars and Mercury. So we're kind of like the crumbs, the leftover tiny crumbs from the formation of the solar system.
Wow. The Earth at this point is actually being formed, a proto-Earth, without the moon even existing.
Yeah, so this time in the solar system, it's total chaos, right? You have all of these bodies orbiting the sun. They're all kind of pulling on each other with their gravity. And so you have this proto-Earth orbiting the sun, and you have this other kind of proto-Mars-sized body orbiting the sun too, and then their orbits overlap, and all of a sudden one day, boom, and they hit each other, and they shear off all this material. And actually, this is really cool because it feeds into your first question of, the distance between the Earth and the moon. Because initially this material, it forms a disk, kind of like Saturn's rings we were talking about, around this new Earth. And that eventually condenses to form the moon, but it's really close to the Earth. The moon, it's like 10 times closer to the Earth than it is today. And since then, it's been gradually moving farther and farther away from the Earth over time.
Huh. So if you were to time travel back to that time where the moon is 10 times closer to the Earth and you looked up in the sky, how huge would it be?
It'd be really big, right? It'd be like 10 times bigger. It would be gigantic. And that has huge consequences for what tides would have been like, right? Because the moon causes tides on the Earth, not just ocean tides, but also rock tides inside of the Earth. It would have been really chaotic because the Earth was still molten, right, at that point too. So it was a pretty crazy time in Earth's history.
Yeah, we wouldn't have been very happy time travelers.
Yeah.
So then why is the moon moving away? Or why did it move away?
Oh, it still is.
It still is moving away.
So it's actually those tides that Briony mentioned, especially the tide that's actually in the bulk Earth. So the rock actually does deform in addition to the oceans. And it's that sort of tidal bulge, the part that's closest to the moon, facing the moon, is tugged just a little bit more strongly than the side of the Earth that's furthest away from the moon. So it raises this like tidal bulge. And the same thing is happening on the moon. So the Earth also raises a tidal bulge on the moon. And those two sort of mass distributions pull on each other in such a way that they tend to slow each other down in their rotation. And that's actually eventually why the moon has come to only show us this one face, because its rotation has been slowed to just be synchronous with the Earth. And because they're slowing down in their rotation, again, because of that conservation of angular momentum, the moon actually has to move out further in its orbit because that angular momentum, it's going into the moon's orbit.
I don't know if I quite got that. So, first of all, what is a tidal bulge, first of all?
Yeah, so basically the part of the Earth that's closest to the moon is basically being pulled toward the moon. And that includes the ocean as well as the rock underneath it. So it's actually deforming the Earth. It's actually making this bulge in the surface of the Earth. So it's the same reason we get tides in the ocean, right? You get these tides every 11 hours passing through the ocean. You get a high tide every 11 hours. And so as the Earth is rotating under the moon, and so that bulge is actually moving along the surface of the Earth over time. And it's basically that process of, creating this bulge and moving it along the surface of the Earth that's gradually draining energy from the system, which makes the moon gradually move away from the Earth.
If you were to look from space above the North Pole at the tides, let's just focus on the water tides, okay? The effect is the same for rock and water and anything that can slosh, frankly. But if you were to watch the Earth from above, you'd notice that the oceans get kind of deformed by the tides of the moon, right? You get a little bit of the oceans poking towards the moon, and then on the opposite side of the Earth, there's kind of a bulge of ocean pointing away from the moon.
No, I didn't know that. That's interesting.
It's not just that the water on the Earth is attracted to the moon, it's that there is a difference between the direction and magnitude of the force from the moon onto the water, depending on where on the Earth you are. For the far part of the Earth, the water feels slightly less force pulling it towards the moon. And if you're on either side of the Earth, not closest to the moon, the direction that you feel a force, it's kind of sideways. And the overall effect is that the oceans get kind of kneaded into maybe a football shape, superimposed on the surface of the Earth. And that's why the tide is higher when you're either closer to the moon on the moon side or on the far part of the Earth. So the height of the ocean above the surface of the Earth changes depending on where you are relative to the moon.
Sorry, but why is water specifically so affected by the moon?
It's because it's liquid. There's no rigidity to it. And so water will flow in whatever direction external forces push on it in order for the overall pressure to be the same. And so the deal is that if the distribution of water was perfectly spherical, the forces from the moon wouldn't be the same everywhere on the surface of the water. And so the water reforms itself in order for the forces to kind of equilibrate, cancel out.
And rock does the same thing, but it's a lot harder to deform the rock to do that, right? And so the scale of the tides of the rock of the Earth are much, much smaller than the ocean.
So if you were to look at this picture of the oceans from above, you would notice that the bulge from the tides isn't really changing relative to the moon. The pointy part of the football is always pointing directly towards the moon. And the reason we get changing tides on Earth is because the moon goes around the Earth once every 28 days, but the Earth spins once a day. So the Earth is spinning underneath that football of water. And so depending on where you are at what time, the tides at your location can be high if you're going through the pointy part of the football, or it can be low if you're going through the flatter parts of the football. So the reason the moon is moving away from the Earth is a matter of coupled rotations. The fact that the tides aren't circulating around the Earth at the same rate as the rock in the Earth means that the tides are kind of kneading the Earth as the Earth rotates under them. And that kneading is a dissipative force. It's taking energy away from the system. So the Earth is going to slow down until its rate of rotation matches the rate of the rotation of the moon around the Earth. But conversely, because of equal and opposite forces, as the Earth feels a force slowing it down its rotation, the moon is going to feel a force speeding up its orbit. And so as the orbit speeds up, it moves farther away.
So is the moon now set in an orbit that it's basically going to stick with, or is it going to, millions of years from now, be even further away than it is now?
It's going to move further away, and the Earth's speed of rotation is going to change and slow down until it's always going to be the same face of the Earth facing the moon, so that this kneading effect no longer occurs.
But that probably won't happen during the lifetime of our solar system. Like, we'll all be destroyed by the sun before that happens, so...
It's a very slow effect.
Oh, okay. Sort of sounds like we're in kind of a Goldilocks zone now, but how many millions or billions of years will it be before, the Earth is no longer in that zone?
I'm pretty sure it's billions of years. Like, it's really, the Earth will be completely destroyed by the expanding, future red giant sun before we get to the point where we lose the moon, basically.
Okay. Those descriptions of the end of the Earth are always so depressing, but yeah.
So the overall idea here is that there's different models for the formation of the moon. And how can we tell which one is right? That's the question, right? Did the moon hatch out of an egg, or did it form at the same time of the Earth? Or is it a passing meteor that got captured in Earth's orbit? Which one of these things is it? And Meg was saying that it was the planet smashing together hypothesis, that there was once a planetoid the size of Mars that ran into the Earth. And that's a pretty dramatic picture. And so the question is, why do we think that's the right one over all of the other pictures? And the deal is that every different scenario that Meg went through at the start corresponds to the moon being made out of slightly different material. So if the moon was made at the same time as the Earth, in orbit around the Earth, then it would have the same constituent material as the Earth does. The Earth has a core made of iron, and then there's the mantle, and then the crust, and that distribution of different types of material would match in the moon. Alternatively, if it was a passing meteor that formed further out in the solar system, its constituent matter would be slightly different. So the idea here is that this collision scenario predicts that the moon would pretty much be made only out of the stuff that was on the outside of the proto-Earth, the crust and the mantle of the proto-Earth. And that's essentially what we see in the moon when we do measurements of what the moon is made out of.
Well, it sort of works the other direction, actually. Really what it is that when we look at the moon, we have several lines of evidence that first, the kind of general stuff the moon is made of is pretty similar to the Earth, right? The general kinds of minerals and their compositions they're mostly pretty similar to the Earth. They're not identical, but they're similar. So that tells us it formed in kind of the same part of the solar nebula. But when we look in detail at the structure of the moon, it has way, way less iron in it. So, the Earth has this big iron core. It's almost half of the Earth is made of this big iron core. And we look at the moon, we know from multiple lines of observation, it doesn't have that. It has a really small iron core. It's mostly made of rock. It's mostly made of mantle, the hot part of the planet that's rock, and then the cool crust on top of that. Whereas the Earth, again, it has this big iron core. And so that tells us that something was different about the way they formed. And so the way to connect that back to the formation models is basically that when you had this planet smashing event, it didn't just smash the planets together. What the model suggests happened was that you had this Mars-sized body that came in and kind of sheared off the top of the proto-Earth, right? Just sheared it off and tore it off. And then the iron of the two bodies kind of came together because it was heavy. And then what was left floating around outside of this proto-Earth was basically just rock, just crust and mantle. And that's what formed the moon in this disk outside of the proto-Earth.
How many billions of years ago was that?
So this was 4.5 billion years or so. And we know that because we have samples of the moon that formed really shortly after this, as well as, the very early samples of the Earth, tiny minerals zircons that have survived for 4.4 billion years since that time.
I mean, when we went to the moon, and I assume brought back moon rocks, what did we learn that we couldn't have learned just by observing it from Earth?
One thing that comes to mind to me is that because I study impact craters quite a bit, and those are the giant circular shapes that are all over the moon, and we have some here on Earth, but not as many. And they're actually our biggest way of keeping track of time in the solar system. By counting all of the impact craters and keeping track of their sizes, we can sort of put together a timeline, like which one came before which other one, and generally sort of which areas on the moon are older than which other areas because they had more time to accumulate impact craters. But that's really a relative timescale. You can only tell things like this section of the moon is older than that section of the moon, but you can't say what the number is that goes with it. So one thing that's really important for just chronology in general and trying to piece together when everything happened, not just on the moon, but everywhere in the solar system, is bringing back these moon rocks gave us a chance to actually use geochemistry to date them to much higher precision, actually, look at the minerals that are in the moon rocks and use radioactive decay to actually get a much more concrete age on those. And that sort of anchors the whole relative timeline that we put together with the impact craters.
That makes sense.
Yeah, so the other really cool thing we learned from the moon rocks, we can't necessarily tell exactly what the mineralogy of a surface is from orbit. That's my job. That's what I do at Mars and the moon. And I'll tell you, there's a lot of stuff we can't see. So one of the things we learned from bringing back moon rocks is that the crust of the moon is actually really weird, right? So when you look at the moon and you look at the man in the moon, the face of the moon that you can see from Earth, you see there's kind of the black spots, right, in the middle, and then it's surrounded by all this white other stuff. And so it turns out those black spots are all big lava flows, flood basalt, huge, huge lava flows, filling all these ancient impact craters. But the white stuff around it is actually the really ancient crust of the moon. And it's made of this mineral called plagioclase feldspar, which is kind of this really white mineral you see in a lot of rocks here on Earth. But it turns out, this is really crazy, the way that crust formed was that you had this molten blob of a moon. And because it was molten, as it started crystallizing minerals out, The lighter minerals floated to the top and the heavier minerals sank to the bottom. And this feldspar mineral is really light, right? It doesn't have much iron in it. You can tell that because it's white. And so the crust of the moon is basically this float crust that formed out of this ancient, what we call a magma ocean that was originally present on the moon. And so when we got samples back from the moon with Apollo, we were able to see that. We were able to see that, yeah, man, these are weird rocks that we really don't see on Earth, because Earth, we don't think, or at least there's no sign that it's preserved of this ancient magma ocean. That's really something that's pretty unique to the moon.
I didn't know that. I just assumed that when the moon formed, it was cold, dead rocks that just formed into a big clump of cold. You're saying that there was like lava and an ocean of magma.
It was literally a ball of magma floating in space.
Huh.
Yeah.
Wow. The thing I love about physics, too, is how visual it is. You know, like I'm imagining like the best special effects in my mind of all of this stuff.
So the topic at hand is, how do we know what the moon is made of on the inside? I mean, at the outset we said, hey, how do we know what kind of material it's made out of? And you go, well, you send the Apollo astronauts and they brought back moon rocks, which we can then analyze and find the answers to some of these questions, right? The Apollo astronauts didn't just bring stuff home. They also left stuff there.
They did. So the Apollo astronauts brought back all these great moon rocks, right? And they tell us all about how the crust of the moon formed. But they don't necessarily tell us a whole lot about the inside of the moon, right? They don't tell us about the interior structure of the moon and all of that. And so the thing they did that was really amazing was they left behind this whole suite of instruments, which included a bunch of seismometers. So seismometers are instruments we use on Earth to measure earthquakes, and the goal here was actually to measure moonquakes, which are, tectonic events, earthquakes, but on the moon. And so, the seismometers, they were just one part of this Apollo instrument package. Every Apollo mission that made it to the surface, so everything but Apollo 13, left behind this instrument package. And it included the seismometers, as well as one of the best pieces of evidence that the Apollo missions did, in fact, happen and weren't just in a movie studio somewhere in the back lots of Hollywood. And this is the Apollo retroreflectors, which are basically these giant mirrors they left behind on the surface of the moon that you can shine lasers at from the Earth. And by measuring the time it takes for the lasers to go from Earth to the moon and back, you can figure out how far away the moon is. But, you can actually do this, with a powerful enough laser here on Earth. And so it's one of the best pieces of evidence that we did actually put people on the moon.
I'll use that next time I talk to conspiracy theories. Yeah. So hold on a second. Sorry to interrupt again, but moonquakes, I thought that earthquakes are because of plate tectonics and the continents shifting around.
Right, yeah. So that's how we get earthquakes here on Earth, right? So on the Earth, we have the crust is broken up into these plates that are moving and kind of running up onto each other and under each other, and the whole crust is really active. So that's actually really rare in the solar system, and there's no other planet that has that. The rest of them are all what we would call a one-plate planet, right? They're not broken up in the same way. So that's actually interesting, right? Because what does that tell us about the history of the Earth? Does that have implications for the why we have life on Earth, right? Because it's an important way to recycle the crust and keep it fresh and keep our atmosphere fresh. But the moon doesn't have that. So the moon doesn't have plate tectonics. So there's no, giant plates rubbing together to make earthquakes. But it does have a lot of other stuff that's going on, right? Like we talked about tides. So the Apollo seismometers that we left behind, so they were active for about 5 years until the late 70s. And so in that time, they recorded, more than 10,000 moonquakes. And the most common ones they saw occurred really deep inside of the moon. They were really weak. So like on Earth, we would call it a magnitude 2 on the Richter scale, which is strong enough that people who are really sensitive could feel it, but most people probably wouldn't. So they're pretty weak earthquakes. And those we think were probably due to tides, right? So the tides from the Earth, deforming the moon, from the moon moving away from the Earth, getting closer and farther in its orbit compared to the Earth. But those are pretty weak. We also see earthquakes, or moonquakes, due to thermal stresses, just, the day-night change in temperature that the moon goes through, sort of changing how big the rocks are, basically shrinking and growing, causing moonquakes. We also see moonquakes due to impacts. So, stuff is still raining down out of the solar system onto the planets. And so that causes moonquakes too. But the really interesting ones that we saw, there were only a handful of these, about 5 or 6 big moonquakes that we saw. These were, magnitude 5 or greater. So magnitude 5 is here on Earth, an earthquake that can cause a decent amount of damage in a place that's not ready for it. Most people will feel that, it'll wake them up. It's a pretty decent sized quake. So on the moon, we saw a couple of these over the period of 5 years. So they're not uncommon, but they're not happening all the time. And these are the ones we think were from really shallow places in the crust. So from right in the crust near the surface. And we think these are actually due to the moon shrinking. which brings us back to our big picture. Hey, the moon is changing, and we know because of these seismometers, the Apollo missions left behind on the moon.
And so was that a big surprise? Like, when did we discover the moon was shrinking?
Yeah, it is. So I think we did not expect to see these bigger moonquakes, but it turns out there are surface features that we see that are due to this, which is really cool, confirming this kind of general idea.
Yeah, so I think that the earthquakes that you mentioned were kind of a mystery for a long time. So that 5 years of Apollo seismometer data, that's from like 1969 to 1970 something. And we've been using that 5 years of data since then to sort of piece together what we know about these moonquakes. And it wasn't until just the last several years when you have this new satellite that's orbiting the moon. It's called the Lunar Reconnaissance Orbiter. And it has some really amazing cameras. And there's been a few other international missions to the moon as well. And with all of this new data, we've actually started to see these features on the surface, which are called lobate scarps. And they're called that because like lobes. So if you look down on the surface, they kind of look sinuous, like they make big sweeping curves and they have like sort of a lip to them. But if you were to sort of like look straight on, like you were going to climb over this scarp, then it would have this like really steep but rounded face. And as you got up over the peak of it, it would sort of level out and be shallow.
It's kind of a cliff that's jutting out over the surface of the moon.
So they found many of these cliffs all over the surface of the moon that we hadn't really seen before because the resolution of the cameras has just gotten much better. And the implication of those, we've actually seen them other places in the solar system. So we think we have an idea of what they're doing. In particular, we think we've seen very similar features on the planet Mercury, which is also shrinking. Actually, Mercury is like a really good example of a shrinking planet because it has a really giant iron core compared to its total size. And that iron core, as it continues to cool, the inside of it, just like our planet, the inner core of that will continue to sort of freeze, go from the liquid phase to the solid phase. And when it does that, it compresses. It goes to a more dense state of matter. So as it does that, you're sort of shrinking the entire radius of the planet. And as you do that, like the surface has to sort of accommodate that. So what happens is you get this like shrinking interior as the whole planet is cooling, and this like rigid crust on top is trying to also shrink, but has to sort of wrinkle itself in order to do that. So on Mercury, we see these really gigantic lobate scarps, and we can use those to kind of estimate how much Mercury has been shrinking since it started forming these scarps. And the really neat thing about the moon is that now that we started to see these there as well, we can start to link that to those mysterious moonquakes that were, this large magnitude would really cause a problem potentially for future structures that we want to place on the moon. So we can sort of start to connect the dots and start to actually see the mechanisms that are behind what we had been observing since the 1970s.
That makes total sense. I understood that completely. It's funny because I was thinking about I wonder how this would affect moon colonies. And I thought, I'm thinking too science fiction again. But I guess that really is something people are keeping in mind.
Yeah, I think, I don't know exactly where the guidelines are, but I believe that that is something that any future long-term structures are going to have to take into account, because that's not a small earthquake at that point of the 5.5 magnitude or so.
Yeah, you imagine San Francisco, right? You have to earthquake-proof all of your buildings. On the moon is an even bigger problem because it's not just that you need to make things structurally sound, it's that you have to make sure you're not going to, burst your air bubble, basically. You're not going to start leaking all your atmosphere into space because you shifted something underneath. So it's a really big deal, and it's something they really have to consider.
I assume that the moon and Mercury are shrinking in such tiny amounts that this will also not eventually affect, the tides or anything else. It's just sort of an interesting fact, right?
Well, on the moon, it's a pretty small amount, so it won't really have a big effect. But on Mercury, it's shrunk a huge amount. It's like tens of kilometers of radius that it's shrunk over the course of the planet's history. So, right now on human scales, it's slow, but for a planet, that's a lot.
So within the scale of human life, that's really not much. But if we were to go fast forward to the future, you would imagine that would Mercury change dramatically because of that?
Probably not, right? You just get bigger and bigger ridges over time.
So these are basically, they're like thrust faults. So like it's on the Earth, we have plates that sort of, shove up against each other and then one will go under the other one. And that's also a kind of thrust fault. It's not the same reason that it's happening on Mercury and the Moon, but it's sort of the same kind of surface feature. So what'll happen is like the section of the crust that's sort of being pushed under the other section will just continue to go further. So you can kind of create a thicker crust eventually by sort of just continuing to shrink and double up everything.
So the Lunar Recon Orbiter, the satellite, was this the purpose of why it was put out to discover this, or was it more of a general, let's see what else we can find out about the moon, and this was a surprise?
So the Lunar Reconnaissance Orbiter, LRO, it was actually partly funded by the human exploration side of NASA, and part of its mission was to scout future sites for human exploration of the moon. So that's actually where part of the money came from. The rest of it was just a general scientific exploration of the moon. I mean, it has a ton of different really cool instruments on board, but the amazing thing that it's done is it's mapped the entire moon at 2-meter or better resolution. So that means we can see, boulders and all kinds of interesting things like that. We can actually see the footprints of the Apollo astronauts as they traveled away from their ships in these images.
Wow, that's really cool.
Yeah, and the thing you see when you look at these images, I mean, it really hits home how little of the moon we've explored. You can actually print out one of these big, we call them LROC, Lunar Reconnaissance Orbiter camera images, lay it down on a table and see this like little tiny postage stamp in the corner that has all the little human footprints in it. And, it's people say, oh, we've been to the moon, we've been there, done that. But man, when you see it in the scale of the actual geology of the moon, we really haven't seen anything yet.
So if we were to land more people on the moon, what would we want to find out by having more boots on the ground, so to speak, that we can't so far just from analyzing it from afar?
Well, so, the Apollo missions ultimately did so much to revolutionize our understanding of the moon, right? Just bringing back, so many samples and leaving behind all of these different science experiments like the seismometers, right, that we talked about. So we could do a lot more of that. We could visit other places, with one of the constraints on the Apollo missions that they had to go to the near side of the moon, right? They had to go to the part of the moon that we could see from Earth so they could communicate really easily. And they wanted to go to the really flat parts because, if you're an engineer at NASA, you want to land in the safest place possible. And so they send you to the parking lots. We have the same problem landing on Mars too, that engineers always want to go to the parking lots and the scientists always want to go to the mountain ranges. So on the moon, we had the same problem. And so most of the places we landed on the moon were actually pretty similar. There were all of these giant lava plains that you can see, again, kind of the dark parts in the side of the moon we see. But we've only sent a few missions that went to other kinds of terrains, basically, like the highlands, this ancient, light kind of white crust. We only had one mission that really sampled those kinds of materials. There's a whole other part of the moon, too, that NASA is trying to get a robotic spacecraft to visit. It's actually the biggest impact crater on the moon. It's called the South Polar Aitken Basin. And we can't really see it from the near side, so we didn't know it was there until pretty recently. But it's this huge impact crater. It goes from the South Pole and kind of curves up the far side of the moon. And it's like a quarter of the size of the moon. It's huge. This was a gigantic impact. And it was actually so big, it dug into the mantle of the moon. It actually dug through the crust into the mantle and excavated the mantle. And so if we could send either humans or robots there to get samples back, that would tell us so much about the history of the moon and how the moon formed. So that's one of the things that NASA's really excited about. And that's a mission that's being proposed right now, and it's called the Moonrise mission. That's the robotic version of that sample return. So the one thing we never talked about, and that was why the moonquakes are important for understanding the inside of the moon.
Okay.
So we didn't really talk about this, but the reason that having these seismometers and detecting these moonquakes was so important is because, the way we interrogate the interior of the Earth is using earthquakes, right? You have an earthquake that happens on one side of the Earth, and then you detect it on the other side of the Earth with a bunch of different seismometers. And by understanding how long it took for that earthquake the signal to get there, you can actually figure out what the wave passed through on its way through the Earth to get to you. And so we can do things like say, oh, we didn't detect earthquakes on this whole part of the Earth. It's because they're being blocked by the liquid part of the iron core on the inside. And you can use that to figure out how big the core of the Earth is, for example. So on the moon, we've done the really very similar thing. We had this network of seismometers for 5 years and measured all these quakes. And by measuring, where these quakes came from and how long it took them to propagate through the moon, we could do things like figure out how big the core of the moon is. And so we figured out that the moon has a core, but it's really, really small. It's much, much smaller than the Earth, which is one of the things that tells us that the moon must have formed in a different way than the Earth did.
I think that made sense.
All right. So you know how, like, if you have a wine glass, you can tap it and tell based on how it rings whether or not it's full of wine?
Yeah, sure.
The more drink that's in the wine glass, the different tone you'll get out of it?
Yeah, that makes sense. Okay.
So essentially what's going on there is the vibrations that come from you tapping it travel through the system differently depending on what's inside of it. So on Earth, one of the reasons we know we've got a big liquid molten core is essentially just paying real close attention to how seismometers in, say, Iowa detect earthquakes that happen in Japan. So an earthquake happens in Japan, that doesn't just make the Earth in Japan rattle. Those vibrations travel through the Earth. They bounce around through the insides of the Earth until we can measure them in Iowa. So from that, we can reconstruct a model of what's going on inside the Earth. And that's how we know on the inside of the Earth there's a big molten core, among other things. So we do the same thing with the seismometers on the moon. You can backtrack how vibrations travel through the moon, and from there you can tell that the moon doesn't have a molten core, and also that the core of the moon is relatively small. Smaller than it would be if the moon had been made out of the same stuff the Earth was originally. Because the Earth has lots of iron in it, so if the moon formed independently of the Earth, it would have the same, say, percentage of iron in it, and you would expect a fairly big core. And that's not what we see. So we know that the moon is mostly made of the rocky stuff that comes from the edges of the planet Earth. So it must have formed by being sheared off of the Earth, the proto-Earth.
Okay. I think I got that. So the moon is shrinking, and this is something that we know because of the moonquake. Is there any other ways in which this is going to affect us on Earth in the future?
So this is completely indirect, but I mean, I think what we were mentioning before about whether this was a surprise that the moon was shrinking, in a certain sense, I think the answer is no, because the way that planets have formed in our solar system's past and the way that we expect them to evolve after that always involves a certain amount of cooling over time. Because when you first put together all of this material to form a planet, you're sort of bringing in all of these pieces from very far away, and they're all sinking into a mutual gravitational well when they come together. And there's a whole bunch of energy that's released when they all do that. So you have all of this gravitational energy that is released when you get all of this material gathered together into a planet. And that's basically the energy that is being emitted over time as that planet evolves. It's sort of it starts at a very hot temperature and then it inevitably cools down over time. And each planet has a different way of doing that based on how much energy it started with and how big it is. So the moon is relatively small compared to the Earth and has cooled much faster. So we can see, the effects of it cooling. But the Earth is cooling as well, and Mercury is cooling, and all of the other planets in the solar system are going through a similar sort of planetary evolution in that sense. So in a very indirect way, I would say that it doesn't affect a lot about our life on Earth to know that the moon is shrinking, but it is a reminder of sort of what all of the planets in the solar system go through and sort of the general lifetime of a planet in general.
At what point in millions or billions of years from now will the cooling of the Earth have any effect on life on Earth?
So the Earth is actually mostly cooling through plate tectonics. And again, plate tectonics is one of the things that makes Earth so fundamentally different from the rest of the planets. And so it has a much bigger impact on what we experience than, the fact that the Earth is gradually cooling. But again, it's kind of the cooling of the Earth that's driving plate tectonics, right? It's the heat in the inside of the Earth that's causing, the plates to move, the plates to subduct, and all these things. So that's really the impact of the fact that the Earth started out hot for us, whereas for the moon, the fact that it started out hot is leading to the fact that it's now shrinking.
Right. So if it's cooling, does that mean fewer or more earthquakes in the future?
So just like Briony mentioned, we're in this plate tectonics state of things because the Earth is so hot that the most efficient way for it to get rid of its heat, to sort of bring the heat up from the core and get it out through the surface, is this convection of the mantle, which is driving plate tectonics. And we don't know of any other planets that have that exact state going on, which is sort of a mystery because there are other planets like Venus that are just as big as the Earth, would have had the same sort of initial heat budget, and it would be more efficient for them to also cool in this way, but they never broke broke up into plates in a way that allows them to actually recycle the crust and get rid of heat as quickly as the Earth is getting rid of heat. So I would say, I mean, eventually it's that cooling rate that is driving plate tectonics. So as the Earth cools, we may fall into a regime where we don't need plate tectonics to most efficiently get rid of the remaining heat that we have. But at what point that would be, I am not sure.
Yeah, at this point, human life may not even exist anymore.
Could be.
Cool. The other really cool thing about plate tectonics too, and one of the reasons we think it might be happening on Earth but not Venus, is the fact that we have liquid water here on Earth. So Venus, as far as we know, it's always been a pretty hot place, and so hot that liquid water has never been stable at the surface. And so we think the reason that Earth might be able to move its plates around and shove one plate under another is the fact that we have oceans and we have liquid water sitting on the surface that can help lubricate this process. And Venus, if it was too hot for that to happen, it never developed plate tectonics. And instead, what we think might have happened with Venus is that instead of having plate tectonics, when it tried to release its heat, just through, more inefficient things like volcanism, it couldn't. And so eventually what happened is that the entire surface of Venus melted. It totally underwent what we call catastrophic resurfacing. And so it actually built up so much heat in its interior that the whole surface melted and reformed. And this is within the past billion years that we think this happened. And so that's actually the fact that we have plate tectonics here on Earth, we think is actually critical for life. First it tells us we had water, but it also means that our surface is relatively stable compared to a planet like Venus's.
There's one more thing that I think is notable in this whole picture. So it has to do with that picture where we talked about the moon moving out from farther away from the Earth, right? That's kind of an incredible claim, isn't it? I mean, to say that the moon's orbit is increasing in width. So is there any direct evidence of that? And there is, and it has to do with these moonquakes, and it has to do with these weird cliffs on the moon. So I want you to imagine deliberately a model where we have these, what are these lunar cliffs called? They're the
lobate scarps.
Lobate scarps, right. So I want you to have an image in your head of these lobate scarps forming. So let's imagine that you wanted to build a soccer ball, okay? You've got a nephew, and he's really into soccer, but you also know he's pretty lazy, and so you don't want to actually spend real money on a soccer ball. So what you do is you go to the dollar store, and you buy a whole bunch of construction paper, and some tape, and a balloon. Okay. And you inflate your balloon and a nice pink spherical balloon. And then you're going to cut out hexagons out of construction paper and then glue them in place. And what you get is a soccer ball. It looks like a soccer ball, right? And then you give it to your nephew, who is maybe a little bit short-sighted and also lazy. And he says, "Thank you. I always wanted a soccer ball." And you go, "Sure, kid. That's $50 I just saved there." So over time, the balloon, because balloons are balloons, it's going to start shrinking. It's going to start letting some air out, right? And so as its radius decreases, the edges of the little construction paper panels that you make, they're not going to fit tight with each other anymore. So instead, they're just kind of overlap and slip over each other. Can you kind of see what I'm drawing in my head?
Yeah, hopefully my hypothetical nephew will have lost interest in that thing by then.
Yeah, right. Exactly. And he will. What a lazy kid. So as it becomes dramatically smaller, these things are going to overlap quite a bit. And those are essentially what we've been talking about. That's what happens on the moon. The crust is solid, but as the radius is shrinking, there's nowhere for these solid chunks to go. The volume the area must contain is shrinking, and so these kind of overlapping plates just kind of shift over each other. If the moon was all alone out in the middle of the void of space, the locations where the crust, the solid surface of the moon that's overlapping to make these cliffs, it would kind of appear randomly over the surface, kind of like when you crack an egg and the egg cracks just go everywhere. Okay, so here's the interesting bit. The moon, as it orbits the Earth, it feels a tide from the Earth the same way we feel a tide from the moon. So the Earth is also applying kind of a kneading force, kind of trying to reshape the moon into the shape of a football, pointing towards the Earth. So where these cracks have occurred is consistent with the tidal forces that the Earth has applied to the moon over its lifetime. So from there we can track the fact that the moon has indeed felt the tidal forces of the Earth and is indeed increasing in orbital radius.
So orbital radius meaning it's moving farther away.
Yeah, that's right.
Yeah.
So in other words, the cracks in the moon that we're tracking, these fault lines, aren't occurring in random locations. They're occurring in locations that are recognizably from the tidal effects of the Earth squishing the moon.
But the moon is not going to move far enough away within any reasonable amount of time that it would really significantly affect the tides on Earth.
Within our lifetimes? Or human lifetimes?
Or even the lifetime. Yeah, I mean, this is something that you were saying before, that by the time the moon moves far away from the Earth, we have much bigger problems to worry about.
Oh, yeah. We're talking about geological timescales here.
Yeah, exactly.
Yeah.
The incredible shrinking moon, everyone.
It's actually kind of an interesting parallel to Mercury, because for a long time we knew that these scarps were there. We were just trying to map them well enough to be able to tell if they were in random orientations or not, and then use that to try to say something about Mercury's history of either slowing down in its rotation, because Mercury is in a resonance also, sort of like how the moon only faces us with one, we only see one face of the moon. Mercury is sort of in a similar situation with the sun, and it had to get into that configuration sometime. So for a long time, we were mapping these scarps on Mercury and trying to look at their orientations to say whether or not they were just completely random, and if they're not random, what do they say about Mercury's past? And I'm not quite sure what the current state of that is right now, but I think that's definitely, there's a paper on that about the lobate scarps on the moon too, tracing out sort of the pattern of tidal forces that you mentioned.
I guess studying any planet is interesting, regardless of whether it's Mercury, Venus, or Mars. Or are there some planets that are definitely more interesting and more relevant to us to study?
I think that depends on your own personal biases, right? So if you look at NASA, right, and you look at where NASA has sent missions, pretty much every major planetary body in our solar system, with the exception of some of the really far out ice giants like Neptune and Uranus, have had dedicated missions. So we've sent a mission to Mercury and Venus and sent a ton to Mars. But if you look at how many we've sent to different planets, you see a huge disparity. So we've sent, one mission to Mercury. We've sent, kind of 1.5 missions to Venus. But we've sent dozens and dozens of missions to Mars over the course of the past 40 years. And that's because, again, we think about really big picture science questions. There's lots of interesting things we can answer by looking at places like the moon about the early formation of the solar system, and Mercury about, what do these weird little planets with giant iron cores look like, and, what do tectonics and that kind of planet look like. But if the question you really care about is what is the history of life in the universe, then there's only a couple of places in the solar system we can really get at that question. And that's been the question that's been motivating not all of NASA, but a lot of NASA science for a very long time now. And so that's why we keep sending missions to Mars. And that's why we're trying to send this new mission to the icy moons of Jupiter, to Europa, because we think it actually has an ocean under this surface layer of ice that we see from Earth and from past missions. And so if you look at, again, they're all interesting. All the planets are awesome, but some of them can answer different questions that some people might prioritize more highly.
Yeah, that makes sense. Yeah.
Well, that was wonderful. Thank you, Meg. Thank you, Briony. You've pleased me. Your efforts have borne fruit, and that fruit is sweet. Here's some fruit, Briony. You get a cantaloupe.
Nom, 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 nom.
And Meg, you get a watermelon.
Oh, nom, 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 nom.
Awesome. I'd like to thank my guest, Eric Molinsky, host of the Imaginary Worlds podcast. Thank you, Eric.
Thank you. Do I have no fruit?
Yeah, well, I mean, you've been dining on their fruit of knowledge this whole time.
You're right. I'm being gluttonous.
Would you like some fruit? I think I've got a potato.
No, I'm good. Don't worry about it. Don't mind me.
Oh,
hey, potatoes are great for Mars.
That's true. That's true. No, thank you. This has been so fascinating and great. Thank you.
You can find links to Eric's work and Meg's work and everybody's work on our website. Hey, everybody, it's announcement time. Okay, first, please give us an iTunes review or tell other people about us online. You know the drill. If people find us on iTunes, they're going to find us because lots of people are giving us reviews. And if they find us online, it's because somebody has gone onto Reddit and told them, hey, there's this podcast you should listen to. It's totally not crummy. On another note, we're still humbly soliciting your donations. Your donations go to paying for server fees and our project to transcribe the episodes as they come out. That's right. Thanks to your support, we've transcribed the entire back catalog. And our newest project is to buy decent microphones for all of the regular titanium physicists. So if you want, you can send one-time donations through PayPal off of our website, or you can go to our sweet Patreon site and give us a recurring $2 donation. This particular episode of Titanium Physicists has been sponsored by a collection of generous people. I'd like to thank the generosity of Randy Rooser, Anne Farnell, and Elise Campbell for their donations. I'd also like to thank Randy Dalzell, Ms. Tina Rautio, the enigmatic Ryan, a TPR Jones, a person named Crux, and Gabe, and Evan Weens, David D., and Dan Vale, a Mr. Alex, WTL, Mr. Per Proden, Andrew Waddington, Mr. Jordan Young, and John Bleasy, a Brittany Crooks, James Crawford, Mr. Mark Simpson, Tucson's Gang of One, Mr. Lawrence Lee, Sixton Linnison, Mr. Simon, Keegan Eade, Adrian Schoening, Andreas from Knoxville, Cadby, John Campbell, Alexandra Zani is great, Winna Brett, Eric Deutsch, Etienne, and a gentleman named Peter Fan, Gareth Eason, Joe Piston, David Johnson, and Anthony Leon, as well as Doug B., Julia, Noah Robertson, Ian, and Stu, Mr. Frank, Philip from Austria, and Noisy Mime, Mr. Shlomo Dalal, Melissa Burke, Yassine Ouarzazi, Spider Rogue, Insanity Orbits, Robin Johnson, Madame Sandra Johnson, Mr. Jacob Wick, Mr. John Keys, Mr. Victor C., Ryan Close, Peter Clipsham, Mr. Robert Halpin, Elizabeth Teresa, and Paul Carr, Mr. Ryan Newell, Mr. Adam K., Thomas Shire, and Mr. Jacob S., a gentleman named Brent Evans, a lady named Jill, a gentleman named Greg, thanks Steve, Mr. James Clausen, Mr. Devin North, a gentleman named Scott, Ed Lowlington, Kelly Wienersmith, Jocelyn Reed, Mr. S. Hatcher, Mr. Rob Abrazado, and Mr. Robert Stiedka. So that's it for Ti-Fi this time. Remember that if you like listening to scientists talk about science in their own words, there are lots of other lovely shows on the Bracula Media Network. Find it through iTunes. The intro song to our show is by Ted Leo and the Pharmacists, and the end song is by John Vanderslice. Good day, my friends, and until next time, remember to keep science in your hearts.
Angela, something I gotta tell you, dear, before you come back here. I lost your bunny. I let him out of the cage. He was eating spring mix on the carpet. Jumped through a window out into the haze. Hopped down Magnolia Boulevard. No way he'll survive.
Now, all these, I mean, of course, this week, I don't know when you're going to post the episode, but this week the big news was about the seven more Earth-like planets that we found. Are all these Earth-like planets so far away that we can't tell if any of them have plate tectonics?
Yeah, so we haven't had follow-up observations yet, because really when you look at planets that are that far away, these are more than 30 light years away, these planets, and so they're really small, right? They're the size of Earth, and so relative to their sun, they're even pretty small. And so we can't really directly observe them yet. That's going to take much more powerful telescopes. But the way that we've been learning about exoplanets, extrasolar planets, alien Earths, in the past has been by looking at their atmospheres, because we can actually see when they pass in front of their host star, we can see the light from that star passing through their atmospheres. And so from that, we can figure out what their atmospheres are made of. And this is how we've determined that there are some planets out there that have water in their atmosphere. Basically, the fact that they have water means that it's possible for them to be habitable for life. And so something that we'll have to keep an eye out for is, I'm not sure if the instrument's powerful enough yet to do this for these planets because they're so small. What are the atmospheres of these planets like? Do we see water, which might tell us about if they have plate tectonics? Do we see evidence for oxygen, right? Which is actually, oxygen is mostly produced by life. And so if we see oxygen in their atmosphere, that could be an indication that there might be life forms on their surface. And so that's going to be the next really big step for looking at these planets.
And so if we do this sort of Moonrise mission and we start having some kind of human habitation or just even sort of scientific labs down there, what are some of the eventual goals once we have set up some kind of human outpost there?
I was going to say what you mentioned earlier about the South Pole Lake and Basin having excavated all the way into the mantle and brought that material up. I think one of the immediate goals there is to sort of understand what that material is like in order to get at the interior of the moon that we don't really have access to otherwise. So that's really exciting because, we can only do so much from the surface. So it's so convenient that this giant impact basin has sort of brought it within reach for us.
Yeah, but then also going back to the moon too, I mean, a lot of it is just about learning how to live outside of the Earth, right? So the moon is sort of the closest place we can go to set up a colony and learn how to live, in a place that doesn't have the atmosphere and all the resources we need right there. So I'm mostly a Mars scientist, and so I mostly look at Mars, and so I really want to go to Mars someday. And there's a lot of arguments that if you go to the moon first, you can learn how to build that colony, how to live off another planet. We need to learn how do you get water, right? How do you mine water on the moon? You need water to survive. How do you build, building materials out of lunar regolith, lunar soil? These are really basic questions that you can go to the relative safety of the moon and test out before you go on to other places like Mars, which for me, the big picture science questions is in going to places like Mars, because I want to know what is the history of life in our solar system, and Mars is one of the best places we can go to understand that, because it used to be Earth-like. We think maybe it used to host life. And so the moon is kind of, in some ways, you can think of it as a staging ground for exploration beyond our Earth system.
I saw an article years ago in Wired about 3D printing like houses and things using the material on the moon, which sounded pretty cool and made sense to me. Is that something people are still talking about?
Yeah, so we're actually doing experiments here at Purdue that directly relate to that. So basically trying to take, lunar soil, this broken up, nasty regolith that's been generated over billions of years by impacts smashing everything on the surface. Can you turn that into a cement and put it through a 3D printer to make bricks and to make roads and pipes and all these different things? Yeah, because one of the big constraints on living on another planet is that it's really expensive to launch stuff off the Earth. And so one of the big goals for NASA and a lot of the international space agencies is to learn how to live off the land on other planets. So yeah, can you do things like mine water on the moon? Can you build bricks out of lunar soil? Questions like that.
Wow. As Tina Fey liked to say in 30 Rock, I want to go there. How many decades, what time frame are we looking at for that to happen?
It depends who you ask, right? So if you ask Elon Musk, he'll be retiring on Mars in his lifetime. If you ask NASA, they're right now, and this of course will change depending on what the Trump administration wants to do, but right now they're talking about going to Mars in the 2030s and actually bypassing the moon altogether. But that wasn't the plan 10 years ago, right? 10 years ago, the plan was to go to the moon, set up a colony, and then go on to Mars eventually. And the problem is it changes with every new president, right? So the president comes in and sets up a plan for NASA, and then NASA has to try to implement that with whatever they have, whatever projects they're already working on. And so like a lot of the work is going on at NASA right now is trying to take the rockets and the equipment they were building to go back to the moon with under George W. Bush. And they were trying to turn that into Mars vehicles to get to Mars under the Obama plan. And now with Trump, there is rumors he wants to go back to the moon. We don't know, right? We'll have to wait and see what happens. But NASA's still building the rocket, so hopefully we'll get somewhere eventually.
But you really feel that the moon, it's much wiser to have the moon as kind of the testing ground, the sort of dress rehearsal.
I don't know. I've heard really good arguments on both sides. One of the arguments against going to the moon is, well, if your real goal is to get to Mars, do you want to risk getting stuck on the moon? Right? There are a lot of people who would argue that we kind of got stuck in low Earth orbit with the International Space Station because it was really expensive to maintain and everybody wanted a piece of it. And so it took way longer to build than we thought. And so there's a risk that going back to the moon, you'd do that too, and you just would never make it to Mars. So there's an argument for let's just go to Mars, we'll figure it out and answer the big science questions by doing that. But, I just want to see us land humans anywhere outside of the Earth. If we went anywhere and had boots on the ground on any other planetary surface, I would be ecstatic. So I'd be happy with any plan.
Yeah, as long as it's not Matt Damon, because I've seen 2 movies now, we've had to rescue him. So that's really not a good idea.
Yeah.
How long is the flight time to the moon?
A couple of days. It took the Apollo astronauts 3 days to get to the moon.
I assume that would be another reason too. Mars is just kind of like Mars is a life sentence, But presumably, until the until flight technology gets a lot better. But I mean, you.
So NASA is trying really hard to make Mars not a life sentence, right? So that's part of the goal, is to figure out how to get humans back from Mars too. But yeah, so that's the big difference too, is that if you go to the moon and you land on it, you can be in constant communication with Earth, right? Real time communication. You can basically have the same kind of Apollo mission thing where it's like, hey, Houston, we have this problem or whatever, and figure it out. But if you're on Mars, you're anywhere from 7 to 20 minutes difference in terms of communication times, right? There's this big lag because Mars is so far away. It takes that long for the radio signals to travel from Earth to Mars. And so basically any astronauts that are on Mars are pretty much on their own. They have to figure out what they're doing, and it's a very different exploration strategy from being on the moon. And it's way more dangerous, right? You can imagine sending a lifeboat to the moon if something went really wrong. It's just 3 days. You could shoot a rocket off. You probably would have one standing by to do that. But man, if you're on Mars, you're totally on your own. And so yeah, there's a huge risk factor with going to Mars.